Dr. Jeff Groh, and this is Calculus 3, or Vector Calculus. What is a vector? Sometimes we like to intuitively think of a vector as a directed magnitude. It has both a direction and a length in some sense. We often draw them as having an initial point, a shaft, and the tip of an arrow, like this. It has a length, and it has some kind of direction, an orientation in space. We can even define certain geometric concepts. We can add vectors by placing them tip to tail, like this, and then drawing in the remaining side on a triangle, we can calculate u plus v. We can even come up with the idea of rescaling a vector. If I add u to u, I should get twice u, which means we should be able to multiply a vector by a real number that rescales the vector to some proportion of the original length. In this case, twice as long as the original length. These geometric notions are not at all satisfactory for the work that we are about to embark upon. We'll need something a little more abstract. What is a vector? Well, by definition, a vector is any element of a vector space. Okay, well, I know that's not very satisfactory either because I haven't told you what a vector space is yet. But keep in mind, what is a vector? A vector is just an element lying in some larger set, a collection of vectors called a vector space. First, a little notation. If I write f maps A into B, I'm thinking of A as the domain of the function f. B is not the range, it's called the codomain. And the range of f is a subset of B. It could be all of B, but it doesn't have to be. For example, if I have f of x equals x squared, I can think of this function as mapping the real numbers into the real numbers. You input real numbers, it outputs real numbers. But the range is equal to the real numbers from 0 to infinity, which is a subset of the set of real numbers. I also realize many of you don't understand the notation for the different number sets. So before embarking on a definition of vector space, let's talk about number sets and their various notations. First of all, we have something called Blackboard Bold N. That includes 1, 2, 3, and so on. These are the natural numbers. Then we have something called the whole numbers. This includes 0. The invention of the notion of 0 was a big milestone in mathematics. Next on the number scale, these are going from smaller number sets to larger number sets. We're going to throw in the negatives. The invention of the concept of negative number was also an important milestone. These are the integers. Now, I know what you're thinking. You're wondering why we're using a blackboard bold Z to represent some number set called the integers. Well, the answer there is that in German, the word is Zahlen, and it was the Germans who invented the notation. Notation is entirely conventional, so it doesn't matter what you choose for your notation. It just helps that you have a notation. What do I mean by conventional? Conventional knowledge is knowledge that is based on an arbitrary choice. Let me give you an example. Suppose we look at various blue colors. There are many colors that you look at and say, well, that's blue. And they're not all just the same shade of blue. They could be a little bit this way, a little bit that way, in terms of brightness or darkness. But they're all called blue. Why? There are an infinite number of different possible colors because the light spectrum is continuous. If that's the case, there are only a finite number of words that you can use for describing colors. Our language is only finite. With that being the case, there has to be some line drawn between the various colors, various color energy spectra there, that makes a division between, say, purple and blue. There has to be some line. Where that line is drawn exactly is arbitrary. And that's okay. As long as we make that distinction, this is purple, that's blue, we can communicate the idea of these different colors to people that we happen to be conversing with. So these arbitrary choices are useful, but they are arbitrary. That's what makes knowledge conventional, based on a convention, some accepted arbitrary choice. What we call these number sets, it doesn't matter. So the Germans chose blackboard bold Z to represent the set of integers. So be it. We'll just go with it. I should mention an important use of the word Zahlen comes from a guy named Kronecker. Kronecker was upset at the work of a man named Georg Cantor. Cantor learned that there are different sizes of infinity. Some infinities are bigger than others. He had names for them. There's Aleph naught, Aleph 1, Aleph 2, using the Hebrew word letter Aleph, the first letter of the Hebrew alphabet, to describe these sizes of infinity. Cantor detested the notion that there are different sizes of infinity, and he actually impeded Cantor from obtaining a position at the University of Berlin. Cantor said, God invented the integers, and man invented everything else. So beyond the integers, those are the inventions of man, but God invented the integers. He used the word Zahlen when talking about the integers in this case. The next number set we're going to talk about are the set of rational numbers. What are rational numbers? Are they numbers that talk and make sense? No, rational numbers are ratios of integers. It's the set of all p divided by q such that p and q are elements of the set of integers, but q isn't 0. Yes, division has that nasty little problem. You're not allowed to divide by 0. That's undefined. So we better make sure that that denominator is not 0, but it's p divided by q, where p and q are both integers. That's the set of rational numbers, the set of ratios of integers. What's the next number set? A lot of my students guess, irrational numbers, but that's not it. It's the real numbers. The irrational numbers are the real numbers with the rational numbers subtracted out. How do we define the real numbers? You're actually not ready for that. It turns out the real numbers can be described as, say, Dedekind cuts. You ever hear of Dedekind cuts? No? Or an alternative way of defining the real numbers is as equivalence classes of Cauchy sequences. Equivalence classes, anyone? Cauchy sequences? No? Well, those are the proper ways of describing the definition of the real numbers, and it's been shown that those two are equivalent to each other. But one way that you can think about real numbers is those are numbers that have a decimal representation. Those having a decimal representation are real numbers. And it can be shown that those that have either a repeating decimal representation or a terminating representation that ends in a sequence of zeros are rational numbers. So the irrational numbers have non-repeating decimal representations. Let me point out that the discovery that the real numbers were the unique, complete ordered field, up to field isomorphism, was an important milestone in mathematics. The characterization of the real numbers as having what are called field properties, properties like the commutative law of addition or the associative law of addition, as well as order properties, A is less than B and B is less than C, then A is less than C, etc., etc. In addition to one other property, the completeness property. Every set that has an upper bound has a least upper bound. The existence of these least upper bounds, that gave us the ability to properly construct the set of real numbers so that we get nice convergence properties for limits. Without that completeness property, we don't have an adequate definition for the set of real numbers that gives us the proper ability to calculate limits and have the limits converge to something that is still a real number. This is something that Newton lacked. He didn't have a proper definition for real numbers, so he could not possibly understand properly the notion of limit. And it took 200 years before mathematicians discovered the appropriate understanding of the set of real numbers, and hence laid the proper foundation for our notion of limits. This completeness property expunged a lot of the paradoxes that kept arising in mathematical theory up until the late 19th century. The next number set we need to talk about is the set of complex numbers. This is the set of all x plus iy such that x and y are real and I is the principal square root of -1. A lot of people don't understand the difference between the square roots and the principal square root. I should mention to you now, the principal square root is always the positive one. When you press that square root button on your calculator, it does not give you plus or minus. It gives you plus. And that's because the symbol, the radical symbol, doesn't represent any old square root. It represents the principal one. For real numbers, the principal square root is the positive one, or 0. For complex numbers, it's the one with the smallest positive reference angle off of the positive real axis. Now that you know about our number sets, we're ready to describe what a vector space is. But be prepared. This is a rather long definition. It involves a lot of parts. The way I enumerate them, there are 10 properties that we have to list. Some professors don't include 2 of these properties because they're kind of implied in the statement at the heading of the definition of vector space. I include them because I like to lay them out there so that you know that they're actually an important part of what a vector space is. A vector space is a set v together with two operations. Now, you've already seen that we need to be able to add vectors together, and we need to be able to rescale them by real numbers. The operations are going to be plus. We can think of plus as a function. It's a function that takes in two vectors and outputs a vector. So the domain is going to be v cross v. V cross v is the set of ordered pairs of vectors. We have the first vector in the sum and a second vector in the sum. It outputs vectors. So addition, vector addition, is a function in some sense. And there's also the other operation called scalar multiplication. Scalar multiplication takes a real number and a vector and outputs a vector. Now, these two operations, vector addition and scalar multiplication, have the following 10 properties as I enumerate them. First is a closure law of addition. This is technically implied by the use of this notation. We say that an operation has closure if when you perform that operation, it takes things in one set and gives you things back in that set. It is theoretically possible to define a notion of addition that takes two vectors in and outputs, I don't know, an animal or a letter of the alphabet. It doesn't have to output a vector. It could output something different. Well, that's not what we're doing here. So we're going to require this closure law. This is actually implied by the notation above, but I'm going to state it as follows. If u and v are elements of the vector space, then u plus v is an element of the vector space. Duh. When you add two vectors, you get a vector. This is not a very high-powered concept. It's fairly simple. Second, we have the associative law of addition. And this too, not a high-powered concept. If u, v, and w are elements of the vector space, we are going to require that u plus v and then plus w gives you the same result if you add v and w first and then u. Duh. Third, we have the commutative law of addition. It says that if u and v are vectors, then u plus v had better equal v plus u. Yeah, of course. Fourth, there has to exist a zero vector. What do I mean by that? There exists some vector which I'm going to write as a 0 with a half arrow over the top. This has to be a vector because it's an element of the vector space, such that for any other u, for any u and v, if you add 0 to u, of course you get the same thing going the other way around, but you just get u. When you add 0 to something, you get the other something. That's how zeros are supposed to behave. The zero vector will behave that way too. But, nota bene, NB is the abbreviation for nota bene, which means in Latin, note well. Zero is not necessarily the same thing as the zero scalar. They may be completely different animals. This is a vector, that's some real number, they may not be equal. So you need to be careful in making distinctions which zero you're talking about. We're going to have at least a couple different zeros floating around now. So make sure that you write the half arrow to indicate which zero you're talking about, if it is the vector zero. And now the last of our strictly additive properties. If you have some vector lying in your vector space, there exists some vector which we'll denote by minus u, such that if you add u to minus u, either way, you get the zero vector. That's how negatives should work, right? Additive inverses. Property 6. We're more than halfway there now. There's the closure law. Of scalar multiplication. Again, this is already built into the definition in the header. If A is a real number, and U is an element of the vector space, i.e. a vector, then A times U gives you a vector. There's also an associative law. Of scalar multiplication. If A and B are real numbers, and U is a vector, then A times B times U gives you the same thing if you multiply the scalars first, and then times the vector U. 8 property of 1. The real numbers have what is called a 1. The vectors don't. But 1 times u equals u. Duh. For all u within the vector space V. The upside down A is the logical quantifier for all. A backwards capital E means there exists. We're getting there. Anytime you have two different operations, you need to know how those operations work together. In particular, we have vector addition and scalar multiplication. How do they work together? Well, if A is a real number, and U and V are elements of the vector space V, what happens if we multiply A times U plus the vector V? And the answer is exactly as you might expect. A times U plus A times V. Duh. And now the last property. If there's a distributive law number 1, there has to be a distributive law number 2. So if A and B are real numbers, and U is a vector, what happens if you write A plus B and then times U? Don't you get A times U plus B times U? Duh. Any set having two operations, plus and scalar times, that satisfies these 10 properties is called a vector space. That may include things that you don't expect are vector spaces. A vector, by definition, is any element of a vector space. And so some things might end up being vectors that you might not have anticipated. Before looking at the typical examples, I'd like to show you some interesting examples. Let C, AB be the set of continuous functions on the domain AB. Is this a vector space? Let's think about it. Are continuous functions vectors? Yes. They satisfy the 10 properties of a vector space. If you add two continuous functions, do you get a continuous function? You know from Calculus 1 the answer is yes. If you multiply a continuous function by a real number, do you get a continuous function? Closure under scalar multiplication? Yes. Is the addition of continuous functions associative? F plus G plus H equals F plus G plus H? Yeah. And F plus G equals G plus F, etc., etc. There is a zero function. The zero function outputs 0 for all x. So you plug in a number, it outputs 0. It's kind of like some people you know. In any case, we have a zero function. There are opposites. F plus its negative yields the zero function. You can go straight down the list. 1 times a function is that function. There's an associative law for scalar multiplication. You go right down the list. All 10 properties are satisfied for the set of continuous functions. So the set of continuous functions forms a vector space, and each continuous function is a vector. We can define some other sets that are also unusual vector spaces. C with a superscript of 1 AB is a set of 1 times differentiable functions defined on the interval AB, and the derivative is continuous. We call these the continuously differentiable functions. Oops. If you add any two differentiable functions, you get a differentiable function. If you rescale a differentiable function, you get a differentiable function. And the other vector space properties follow from the fact that the set of differentiable functions is a subset of the set of continuous functions. We can write the set of continuous functions AB contains as a subset the 1 times continuously differentiable functions. In fact, we sometimes write not equal to, because every function that is differentiable is continuous. But there are continuous functions that are not differentiable. Think of the absolute value function, for instance. Well, if there are C1 functions, how about C2 functions? 2 times differentiable, having a continuous second derivative. Those are a proper subset of the set C1. And C3. We can keep going. The infinitely differentiable functions. And we can even keep going. The analytic functions. Do you remember those? From Calculus 2. The set of functions representable by a power series having a positive radius of convergence. Yeah. Back in Cal 2. Sine, cosine, e to the x. All these functions are analytic, which means they are automatically infinitely differentiable, but they have an additional property. They're expressible as a power series. I always teach my Calculus 2 students an example of a function that's C infinity, but not C omega, not analytic. There is the classic example of the function e to the negative 1 over x squared when x is not 0, and 0 when x is 0. This function is not analytic at 0, but it is infinitely differentiable. So I would like to begin a discussion of some simple vector spaces with the vector space R2. This is the set of all angle bracket x comma y, such that x and y are elements of the set of real numbers. This describes a set. I also need to describe the two operations. AB plus xy is, because I said so, a plus x, b plus y, and a times xy is, because I said so, ax comma ay. Let's see if these two definitions are consistent with the definitions that we gave earlier geometrically. You can see that if I have the vector 2 over 1 up, and add to that a vector that moves 1 over and 3 up, so I'm taking the vector 2, 1, and adding the vector 1, 3. According to my definition, I should get the vector 3, 4. And in fact, drawing in that remaining side of the triangle, I do in fact get the vector 3, 4. So this definition of vector addition is very algebraic. There are huge advantages to going from geometric to algebraic notions. The algebraic notions are almost always a lot easier to deal with. We go from adding in the side of a triangle to just adding the coordinates. It just reduces the notion of vector addition to the notion of addition of real numbers. What about the notion of scalar multiplication? Suppose we have the vector 1, 2, and we multiply that by 2. I should go over 1 up 2 again. That should give me the vector 2, 4. Both geometrically and algebraically. So these two notions of scalar multiplication and vector addition are consistent with those old geometric notions. Let's look at vector subtraction. The geometric notion of vector subtraction, as you place the vectors tail to tail, and then draw in the remaining side to get, say, v minus u, where the tip of the subtraction is at the tip of the first vector in the subtraction. This, by the way, is consistent with the notion of vector addition, because you place vectors tip to tail when you add them. If I add u to v minus u, I had better get v. Right? Consequently, vector subtraction is not a primary notion, it's a secondary notion derived from our understanding of addition. Algebraically, if I have a vector xy, and I add that to the vector negative x, negative y, that gives me the vector 0, 0. Note that if I add 0 to any other vector, I get the other vector. The 0 vector in this case is the vector with two coordinates equal to 0. Note that that is not the 0 scalar. Those are two different things. You need to be very careful to make that distinction between the 0 vector and the 0 scalar. It follows then that the negative of a vector is the same thing as negative 1 times that vector, which is found by taking the opposite sign on each coordinate. If I want to subtract u minus v, that's the same thing as saying u plus negative 1 times v. So again, subtraction is addition of the opposite, as per usual. R2 is a two-dimensional vector space. You have 2 degrees of freedom, 2 degrees of wiggle room, x and y. Isn't there a possibility of an R3? Defined in the obvious way. With the obvious operators defined in an analogous way with R2. What about R4? Couldn't we have an R4? Becoming a little tedious, but how about W, X, Y, and Z? Notice I'm not putting any connotation here about the fourth dimension being time or anything like that. I'm just saying there's one more degree of wiggle room. Why not 5 dimensions or 10 dimensions? Do we have any trouble at all mathematically constructing such a notion? The only problem is notation. Let's write x1, x2. Let's keep going until we get to x10, such that all the x sub k's are elements of the set of R, with the appropriate notion of vector addition and scalar multiplication. We have no trouble coming up with whatever dimension you'd like, mathematically. Algebraically, we have no problem. Drawing it, that's another problem. But any dimension at all, including infinite dimensions, is no longer a problem. Before moving on, I would like to address a few issues that apply to vector spaces in general. First, in any vector space, there is one and only one zero vector. We have not assumed this. We assumed the existence of a zero vector, but we haven't assumed that that zero vector is unique. We need to show that. That does follow from the vector space axioms that we have assumed. The proof is very interesting because it is similar to all uniqueness proofs. You assume there are two of something, and then prove they have to be equal. Suppose 0, 1 and 0, 2 are zero vectors. In the vector space V. Then, if I add 0, 1 to 0, 2, I must in fact get 0, 2, since 0, 1 is a zero vector. Also, 0, 1 plus 0, 2 must be 0, 1, since 0, 2 is a zero vector. Every equivalence relation is reflexive, symmetric, and transitive. By the symmetric property of equality, 0, 1 will be 0, 1 plus 0, 2. Then, by transitivity, since 0, 1 is 0, 1 plus 0, 2, and 0, 1 plus 0, 2 is 0, 2, 0, 1 equals 0, 2. Therefore, the zero vector in a vector space is unique. Another basic theorem, which might seem obvious, but we have not assumed this, is that if you rescale a vector by 0, you in fact get the zero vector. The proof goes like this. Let's take 0 times u, and note that 0 plus 0 is 0, so these two must be equal. But by the distributive law, we get 0 times u plus 0 times u. Now, every vector has an inverse. You can add the inverse of 0 times u to both sides. And we'll add that to the other side as well. Making sure that we have associated these two vectors because we're adding them first. But by the associative law, you can reassociate that sum on the right. And by the definition of additive inverse on the left, you must get the unique zero vector. This first grouping on the right-hand side now also is equal to the zero vector. And when you add the zero vector to anything else, you get the other thing. And that's the end of the proof. These last two theorems work for vector spaces generally. You now know an infinite number of different vector spaces, not just R2 or R3. There's C1, C2, and so on. Rn, where n is large, you can have as many dimensions as you'd like. These theorems work in any vector space. I'd like to go back to R2. There's some additional concepts I would like for you to know. We're going to make some definitions. And let's suppose we have a vector 1 unit in length in the direction of the positive x-axis. We're going to give that vector a name and another name to the vector 1 unit in length in the direction of the positive y-axis. We're going to define I, which I'm going to get a little hat. This is a definition. You accept definitions, you prove theorems. It's the vector 1, 0. The vector j is, because I said so, the vector 0, 1. Now I want you to see something. If I have a vector xy, I can definitely rewrite that as the vector x comma 0 plus 0 comma y. Now, by scalar multiplication, I can rewrite this sum as x times the vector 1, 0 and y times the vector 0, 1. Every vector xy can also be expressed as x times I plus y times j. These are equivalent notations. There are certain advantages to using each. Many of you may have seen this I, j, and then in 3 dimensions k notation before. I want you to be comfortable with the angle bracket notation too. You'll find that it's very useful. Now we're going to define a notion that gives you the length of a vector. Suppose the tip is at the point xy for some vector u. Drawing a altitude here, we get x and y. Now the length of the vector is going to be denoted by something called the norm of u. We'll make this a definition. The norm of some vector u, which has coordinates x and y, is denoted by this double bar. Now, I have to be honest with you. A lot of texts will use a single bar notation. In my humble opinion, that gives rise to confusion, because if you see the double bars, you might think absolute value. You would have to interpret it contextually that it's applied to a vector, and therefore it's not the absolute value, it's the norm. So, to make that distinction absolute, I'm going to use this double bar notation. It's the norm for sure. It gives you how long the vector is. It's defined the way that you would probably define it. The norm of that vector xy is calculated by the Pythagorean theorem, the square root of x squared plus y squared. I like to put a little downward flange at the end of my radical symbols. The reason for that is that we need to be sure exactly where those radicals end. Students often write these square roots imprecisely. It's unclear where that square root ends for sure. To avoid your bridges falling down in the future, to clearly communicate not only to others, but even to yourselves, you need to put the downward flange at the end of that square root. I have an old calculator, and on that square root button, it's written with that downward flange. It's good engineering practice. I want you to do that. Let's do an example. Suppose I'm taking the norm of the vector 3, 4. Well, shoot, 3 over 4 up. Better be 5, 3, 4, 5. It's the square root of 3 squared plus 4 squared. That's the square root of 9 plus 16, which is the square root of 25, or in other words, positive 5. Suppose I have the vector u that is 3i plus 4j. This is the same vector as in the last example. It's just using an alternative notation, but I want you to be careful. I and j take no part in this process. So this will be 5 just as before, but leave the I and the j out of it. We have this new object called the norm. We need to investigate the properties of this object, and that's the point of the next theorem. When I introduce a concept, I like to define it. I like to operationalize it by giving you an example. How do you do it? I like to describe the algebraic properties and then the geometric properties. Well, the geometric property in this case is built in. It's giving you that Pythagorean length of an object. Pretty simple. What's missing so far is the algebraic properties. We're going to have the following set of properties. First of all, pretty obvious, you can't get a negative length. Those are out. This norm is defined in terms of the principal square root. Remember, the radical symbol doesn't mean any old square root. It means the principal one, and that's the non-negative one. And under what conditions can the length be 0? That can only happen if u is the 0 vector. The norm of a constant times a vector, what happens to the constant? When you define a new object, you need to define how it works in relation to the other operations that you've defined. We've defined prior to this point scalar multiplication and vector addition. How does the norm operate in the presence of these two operations? And the answer is scalars come out of the norm, but they come out in absolute value. It's important that you have absolute values around that scalar k. And finally, we have what is called the triangle inequality. We'll show this in a moment. Let's go back up and look at property number 1. The norm of xy is the principal square root of x squared plus y squared by definition. And since we're dealing with the principal square root, this must be non-negative. Suppose then that the norm of xy is 0. That's true if and only if 0 is the square root of x squared plus y squared, which is true if and only if 0 is x squared plus y squared. The only way you can get a 0 square root is if the thing under the radical is 0. But wait a minute, x squared is not negative, and y squared is also non-negative. If you add two non-negative things together and get 0, both terms going into that sum must in fact be 0. This is true if and only if x squared is 0 and y squared is 0, and that's true if and only if x equals y equals 0. And finally, if both coordinates are 0, our vector u is the vector 0, 0, the 0 vector. On property 2, we have the norm of a constant times some vector, which is, by definition of scalar multiplication, the norm of kx, ky, and by the definition of the norm, that's the square root of kx squared plus ky squared. You can rewrite that as k squared x squared plus k squared y squared, which factors as the square root of k squared times x squared plus y squared. Now, provided the factors under a radical are not both negative, the square root of ab is the square root of a times the square root of b. Again, a and b not both negative, but these are both positive, or 0, which means we can write this as the square root of k squared times the square root of x squared plus y squared. What is the square root of k squared? I always try to trap my students in this. It's not k. It's the absolute value of k. Who lied to you and told you that this is k? It's not. If k is negative, say negative 2, negative 2 squared is positive 4. The principal square root of positive 4 is positive 2, not negative 2. You never get negatives out of the principal square root. You have to get the absolute value. And so what we have here is the absolute value of k times the norm of the vector xy. Scalars pull out of norms in absolute value. Do you want to know where your misconception about the square root of x squared equaling x came from? Way back in Algebra 1, your Algebra 1 teacher said, the square root of x squared is equal to x, provided x is greater than 0. So under his or her breath, your Algebra 1 teacher said, provided x is greater than 0. Yeah, square root of x squared is x, provided x is positive. They tacitly assumed you were dealing with positive numbers so that you didn't deal with all kinds of nastiness involving absolute values and things like that. They systematically avoided it. We can no longer avoid that. The third property we call the triangle inequality. It follows from a principle from high school geometry. Let's suppose we have a vector u, and to this we have a vector v that we can add. This remaining side is the vector u plus v. These vectors form a triangle. The length of each side is the norm. Principle in high school geometry says that the sum of the lengths of any two legs of a triangle is greater than the length of the remaining side. Put into the form of an inequality, that says the remaining side has to have a length that's smaller than the sum of the lengths of the other two legs in that triangle. But we have a strict inequality here. How do we get the conditional inequality, or equal to? And the answer is the triangle inequality applies for triangles, but what if you don't have sides that represent a triangle? It is possible to get equality if you don't actually form a triangle. Instead, you form kind of a line segment. And so equality is possible in our case, and that's the end of the proof. This follows from that high school geometry principle. The sum of the lengths of any two legs of a triangle is greater than the length of the remaining side. Let's do some basic things. Find a vector from -1, 3 to 4, 7. Let's see. Negative 1, 3 would be here. 1, 2, 3, 4. 4, 5, 6, 7 would be here. We want to find the coordinates of this vector. Notice that you're going 5 over and 4 up. This vector, if I call this the point P and this the point Q, we can denote the vector that goes from P to Q by writing PQ with a half arrow over the top. The way to get a coordinate representation is to subtract the coordinates. So you can see that we get the vector 5, 4 over 5 units and then up 4 units. So very simple. Subtract coordinates from the terminal point to the base point. Terminal point minus base point. Terminal point minus base point. And that gives you the coordinates of the vector. Very simple. As another example, suppose u is the vector, say, 2, 5, and v is the vector negative 4, 1. Let's find 3u minus 2v. Let's do this one step at a time. Be careful. 3 times u, that's going to be what? 6, 15. And 2 times v, negative 8, 2. Then we subtract coordinate-wise. 6 minus negative 8 is 14. And 15 minus 2 is 13. Find the norm of u if u is the vector 2, 5. In our solution, we use the definition. We'll square the coordinates, add them up, and then take the square root. We'll get the square root of 4 plus 25, and that is the square root of 29. I should mention something about this little square root with the little downward flange at the end. I remember distinctly in 4th grade learning about apostrophes. Possessive case, the plural case. Where do you put those apostrophes? The plural possessive case. It was all very confusing to me in 4th grade. So I tried to fool my teacher by putting the apostrophe right over the middle of the S, and hopefully my teacher would let me get away with it. I did get away with it often enough, but that's just showing that I wasn't careful about learning that concept and knowing exactly where those end. I wasn't careful about learning exactly what that concept of the apostrophe was and how to use it in 4th grade. Don't communicate as ineffectively as I did with my apostrophes in 4th grade. Instead, communicate very clearly where those square roots end by putting a downward flange on it. A unit vector u is a vector having norm 1. The norm has a value equal to 1. As you can see in R2, there's going to be a whole lot of different unit vectors. Every vector with the base point at the origin and the tip on the unit circle is a unit vector. Note that I is a unit vector, and so is j. I points one unit into the direction of the positive x-axis, and j points one direction into the direction of the positive y-axis. They're both unit vectors, but there are many other unit vectors. To normalize a vector v is to find a unit vector u in the same direction as v. In other words, u is a scalar times v, where that scalar is positive and the norm of u is 1. We're going to use this concept throughout the rest of the course. So you're going to need to know how to operationalize this definition. We'll do that next. The vector u, defined in the normalization process, is 1 over the norm of the vector v times the vector v. By an abusive notation, we will often write that as v over the norm of v. Technically, there's a scalar out front, and it has to be multiplied on by scalar multiplication. But it is customary, conventional, that we may write it as v over the norm of v instead. You can see that if I take the norm of 1 over the norm of v times v, that scalars can come out of norms in absolute value. But the absolute value of a norm is itself, because norms don't give negative values. So this scalar 1 over the norm comes out, leaving just the norm of v inside. Well, the norm of v cancels in each case, in which case you get a length of 1. So this will be a positive scalar multiple of the vector v having length 1. This is how you normalize a vector. For example, suppose you are instructed to normalize the vector v equal to 3, 4. You already know that the norm of v is 5, because we have a 3, 4, 5 Pythagorean triple. So u is v over the norm of v, or 1/5 times the vector 3, 4, which gives us 3/5, 4/5. It's easy to check that the vector 3/5, 4/5 has norm equal to 1, length equal to 1. Before getting to the important examples, I need one more notational thing. Let's suppose we have some vector v. It has a particular length, described by the norm, but in R2, it also has something called a direction angle. The direction angle will be measured positively when swept out counterclockwise, beginning at the positive x-axis and terminating with the vector. Now, I'll drop a little altitude here and label the other sides of this triangle x and y. I want you to notice something. X divided by the norm of v would be adjacent over hypotenuse. Adjacent over hypotenuse is the cosine of the direction angle. Opposite over hypotenuse opposite over hypotenuse is the sine of the direction angle. We'll solve these two equations for x and y. X is the norm of v times the cosine of the direction angle theta, and y is the norm of v times the sine of the direction angle. If v is x comma y, which is our notation, then that's the norm of v times the cosine of the direction angle, norm of v times the sine of the direction angle. The scalar norm of v can be factored out. And the original vector v can be expressed as its length, the norm of v, times the angle bracket vector cosine theta sine theta. I want you to think about the length of this vector, angle bracket cosine theta sine theta. The norm of cosine theta sine theta is the square root of cosine squared theta plus sine squared theta. But by the Pythagorean identity, cosine squared theta plus sine squared theta is equal to 1. So this part has magnitude 1. This part is the length of the vector, the norm. This way of expressing a vector decomposes it into a direction and a magnitude. This is going to be awesome when it comes to solving applied problems. You're going to find that this equation right here will greatly simplify the solution of a lot of vector problems that would be very difficult to solve geometrically. They will be trivial to solve algebraically, but you have to use this equation. I want to look at a simple example. Suppose we have an airplane. The airplane is flying in a particular direction. What an awesome drawing of an airplane. This is amazing, right? Let's suppose the nose is pointed 10 degrees north of due east, and the airplane is flying at 450 miles per hour. So we have a direction angle. Notice I'm giving the direction angle instead of the heading or the bearing. I want to conflate a lot of external issues. Let's just get right to the mathematical points. The airplane is pointing in this direction and heading at 450 miles per hour, but it's experiencing a crosswind. The wind is at 75 miles per hour, and it's in a direction which is, let's say, 15 degrees south of due east. What is the resulting ground speed and direction angle of the airplane relative to due east? How is this wind blowing the airplane off course? You might have sat at the end of an airport runway and seen airplanes coming in for a landing, and on a strong crosswind, the airplanes come in at quite an angle to the runway. They have to set up what is called a crab. You get a little crabby. When crabs walk sideways, the airplanes turn a little sideways into the wind in order to maintain their direction in the direction of the runway, fighting that crosswind that's blowing across the runway. So what's happening here is the plane is being blown off course. How far off course is it? And what is the resulting ground speed? Here's what we'll do. We'll have the air velocity vector and a wind velocity vector versus the ground velocity vector. the ground velocity vector will be the air velocity plus the wind velocity. Well, what is that? Remember how we decomposed these vectors? We did the magnitude times the vector with the cosine and the sine of the direction angle. A is going to be 450 miles an hour times the cosine of 10 degrees sine of 10 degrees. The wind is going to be 75 miles per hour. The cosine of negative 15 degrees, the sine of negative 15 degrees. Don't forget those negatives in there. They're important. It's negative because we said you get positive angles when measured counterclockwise. The angles measured clockwise off of that positive x-axis direction, the angle is negative. We're going to add these two to get A plus W. What we'll do is we'll multiply this scalar onto each of these coordinates. Crunch those numbers on our calculator, add them up, and see what we get. Now, according to my calculator, we get 515.6. We'll give this to the nearest tenth of a mile per hour at this level. And for the y-coordinate, I'm getting 58.7. The units are, of course, miles per hour. So I now know the ground velocity vector. Velocity is a vector quantity. Speed is the norm of the vector. So to find the ground speed, I need to calculate the norm of the velocity vector. The ground speed is, according to my calculator, calculating the square root of 515.6 squared plus 58.7 squared, 518.9. We'll call that 519 miles per hour. Now, when I put a dot over an equal sign, that has a particular meaning. What I'm trying to convey to you is not that I'm getting something approximately equal to, but rather that this is accurate to some decimal place rounding. I'm saying this is a rounded answer, and so you can see how this is rounded. The dot over the equal sign conveys a particular meaning. Make sure that you understand what I'm trying to say there. So the ground speed is 519 miles per hour. That side wind gave the craft a little bit of a boost in addition to knocking it out of its direction a little bit. But what is the direction? Note that if I have some vector with coordinates x and y, with the direction angle theta, then the tangent of the direction angle will be y divided by x. In this case, we get the tangent of the direction angle is 58.7 divided by 515.6. Since the direction angle is going to be in the first or fourth quadrants this time, we can use the inverse tangent to calculate this. It'll be in the first quadrant because we have positive over positive. Tangent is positive in the first quadrant, negative in the fourth quadrant. So theta will be in the first quadrant. We can just take an inverse tangent of this ratio to calculate theta. And I'm getting about 6.5 degrees, keeping my calculator in degree mode. So the airplane has its nose pointing in the direction 10 degrees north of due east. It's experiencing a crosswind and the airplane is traveling in the direction 6.5 degrees north of due east. It's traveling with an airspeed of 450 miles per hour, but with that 75 mile per hour crosswind, the ground speed is about 519 miles per hour. I just want to do a couple more examples today. These examples will relate to statics. In a statics problem, when you add up the forces in the problem, they have to add up to the zero vector. So there's no net acceleration because the sum of the forces is the zero vector. So I'm going to give you the evil sister problem. Suppose we have a child sitting on a swing, holding on, and the child is being held back by his evil sister. The sister is pulling straight back on this child, who happens to weigh, let's say, 50 pounds. That weight is a force going straight down. The child is being dangled, his little feet dangling down, at an angle of 60 degrees, the precarious angle of 60 degrees, and the sister is happy. Now, there is another force that is acting on this child, and that is the force of tension in the ropes of the swing. There are three forces involved here. There's the sister force, there's the tension force, and the gravitational force. And if the child is just being dangled there, feet dangling in the air, not being allowed to swing back and forth, just motionless, then we have a statics problem. The sister force plus the tension force plus the gravitational force must equal the zero vector. Let's think about these forces. First of all, the tension force. If we draw a little horizontal line here, the tension force has a direction angle equal to not 60 degrees, but the complementary angle of 30 degrees. So whatever this tension force is, we know it has some magnitude. Our goal is to find the magnitude of the tension in the rope and the magnitude of the sister force. Let's try to find those two things. We're going to have the cosine of 30 degrees sine 30 degrees. The sister force goes straight back. It has no vertical component. So it's going to be minus the magnitude of the sister force, comma, 0. No vertical component, all horizontal, all pointing in the negative axis direction. The gravitational force is straight down. It has no horizontal component, and 50 pounds straight down. So here's our setup. All of these have to add up to the vector 0, 0. That's going to give us two equations. You can see, first of all, cosine of 30 degrees is the square root of 3 over 2, and the sine is 1/2. We'll get the norm of the tension force, one of the things we're solving for, times the square root of 3 over 2, minus the norm of the sister force, plus 0, must equal 0. Also, 1/2 times the norm of the tension, plus 0, minus 50, is equal to 0. If we solve then this system of two equations and two unknowns, we can have the magnitude of the tension of the rope and the magnitude of the sister force. First of all, the magnitude of the tension in the ropes must be 100 in order to have the second equation be satisfied. There's 100 pounds of force being supported by that rope. The rope had better be of a quality sufficient to handle 100 pounds of force. Sisal rope is usually about 500 pounds capacity, so shouldn't be a problem. And if a chain is used, then it has even more capacity. Knowing now that the norm of the tension in the rope is 100 pounds, we'll plug that in here. We'll move this over to get the norm of the sister force. Is root 3 over 2 times that 100, or 50 root 3 pounds. My calculator tells me that the sister force is approximately 86.6 pounds. So that must be one strong sister to be able to pull back with 86.6 pounds of force on this 50-pound child dangling his legs down in the ground, but at an angle of 60 degrees. Let's try another example. Let's suppose we have a ceiling and two cables holding up an object that weighs 1,000 pounds. Let's further suppose that the angle from the ceiling on the left is, let's say, 45 degrees, and on the right is 60 degrees. We have two cables holding this object up, so we must have a tension 1 and a tension 2 in addition to the force of gravity. We will assume that this is a statics problem, meaning the cables have enough power to hold this thing up without breaking. We're not going to allow this to break. It's going to sit there and be just secure. I want to know the magnitude of the tensions in these two cables. Keeping in mind, this is a statics problem, so the norm, so tension 1 plus tension 2 plus the force of gravity must equal the zero vector, 0, 0, just as in the last problem. I want you to pay careful attention to this problem because this looks like a pretty good exam type problem. First of all, tension 1. I don't know what its magnitude is, but I do know its direction. If I draw a horizontal line here, this direction angle is going to be pointing into the second quadrant with a reference angle of 45 degrees. It's going to be 135 degrees. So I'm going to have the cosine of 135 degrees, comma, the sine of 135 degrees. Now, how about tension 2? If the angle up here with the ceiling is 60 degrees, here we have parallel lines cut by a transversal. Alternate interior angles are equal, so its direction angle is 60 degrees. So we'll have the cosine of 60 degrees, the sine of 60 degrees. The force of gravity operates straight down, so its x-coordinate is 0, and the y-coordinate must be negative. If we add all these up, they have to add up to 0 in the first coordinate and 0 in the second coordinate. That should give us two equations in the two unknowns, the norm of T1 and the norm of T2. Adding up those x-coordinates, we have negative root 2 over 2 norm of T1 plus 1/2 norm of T2 plus 0 equals 0. Then positive root 2 over 2 norm of T1 plus square root of 3 over 2 norm of T2 minus 1,000 equals 0. We have then two equations in two unknowns. we should be able to solve them. Multiplying the first equation through by 2, we can solve for the norm of t2. The norm of t2 is the square root of 2 times the norm of t1. Moving this to the other side. We can substitute this into the second equation. First I'll move this over. We'll have root 2 over 2 times the norm of t1. Keeping in mind that the norm of t2 is the square root of 2 times the norm of t1, I'll have plus the square root of 2 times the square root of 3, that's the square root of 6 over 2 times the norm of t1, equals 1000. We can multiply through by 2, and that will give us 2000. Factoring out the norm of t1, we'll have root 2 plus root 6 equals 2000. Dividing the additional factor off, we have the norm of t1, the magnitude of the tension in the first root, is 2000 divided by square root of 2 plus the square root of 6 pounds. We can then plug this value into the equation up here and get the norm of the tension in the second root is 2000 times the square root of 2 divided by root 2 plus root 6. Crunching these numbers on my calculator, I get the norm of the vector t1 is 517.6 pounds, rounded, and the norm of the tension in the second row is 732.1 pounds, rounded. I want you to think back about how it is that we solved these applied problems. These problems were made very simple using the formula V is the norm of V times the cosine theta sine theta. The use of this formula made trivial, it turned complicated geometric problems into trivial algebraic problems. And from there we could solve these complicated statics problems or low off course problem. So we owe it to this little representation of vectors here.